Welcome back to this lecture series on pulse width modulation for power electronic converters. So, for most part of this course is going to be on how are you going to produce those pulse width modulated waveforms for various power electronic converters and to be able to analyze the effects of those waveforms. So, but firstly we have been discussing about power electronic converters now. So, we earlier discussed about DC to DC converters, then we moved on to DC to AC converters, and in which we dealt with the traditional voltage source inverter and the current source inverter. And today in this lecture we are going to be discussing so called multi-level converters or multi-level inverters. These are also voltage source inverters. So, first what we will be doing is we will be briefly reviewing the voltage source and current source inverters, which we looked at in the previous lecture, namely the third lecture. So, this is a single phase voltage source inverter. It is quite obvious if you see that you have a voltage source here. So, you have a voltage source, this is a DC voltage source. This can convert DC into AC because you can very clearly see that if the switches are connected as shown here like this and here, A can be positive with respect to B. If the switches are connected the other way as shown by these dashed lines, then you can have B positive with respect to A. If both the switches, let us say both A and B are connected to the top DC bus or both of them are connected to the bottom DC bus, then the voltage across the switch can be 0 2. Thus, you have voltages of plus minus VDC are 0. These are the three different instantaneous voltages possible across this. Since you have this positive VDC as well as minus VDC applied across this, you can see that it is actually what you get here is an alternating voltage. So, you get an AC voltage here. Now, this AC voltage we will ensure that does not have any DC component. It may be non-sinusoidal, but it will not have any DC component. So, it will have only various sinusoidal components. Each of those sinusoidal components will produce some amount of sinusoidal current. Let us assume the load to be linear. So, when you say the load is linear, you apply a sinusoidal voltage on that, it will draw a sinusoidal current of the same frequency. So, the load voltage may have sinusoids of different frequencies, the fundamental and the harmonics, etc. We will be dealing with them later in greater detail. There will be corresponding sinusoidal currents of various frequencies, the fundamental and the higher harmonics. All the fundamental and higher harmonics added together would be some kind of an alternating current waveform, which may not be exactly sinusoidal. It can get closer to a sinusoid if you do a good modulation, if you do it at a good switching frequency, but well, it is going to be a sinusoidal, it is going to be an alternating current now. So, you have an alternating voltage applied across the load and alternating current flowing through the load, hence this qualifies the name inverter, because what you have is DC, what gets applied on the load is AC. So, it qualifies the term inverter now. So, it is a voltage source inverter because the DC source is available as a voltage source here, it is available as a voltage source. So, it is a voltage source inverter. And why do we call this a single phase voltage source inverter? Because the load is a single phase load. So, this is a single phase voltage source inverter. Many a times this voltage source inverter is abbreviated, and we use the acronym VSI to denote, indicate a voltage source inverter now. So, this load we presume that it is inductive, it could be an RL load. Sometimes it can also be an active load, meaning there can be RL and a back EMF being connected here. It could be basically some kind of a single phase motor kind of a source could be connected here. That it is also possible that this, but we presume that the load is inductive in nature, and an inductive current should never be snapped open. The inductive circuit, in an inductive circuit, path should be provided for the current to flow through. You can't just open out an inductive circuit. So, what do we do? There a load has two terminals and both the terminals A and B are connected to the poles, one pole each, and now you want a potential of either you want to connect either your positive DC bus here or the negative DC bus here, hence you have a single pole double throw switch and the DC source is connected across the throws. The load terminals are connected to the poles, the load is inductive here, they are connected to the poles and the DC voltage is connected across the throws. These are the throws, The DC voltage is connected across the throws. Similarly, the DC voltage is connected across these two throws. So, what you need is, you need certain switches which can function as a single pole double throw switch in this environment. So, the current basically can be in either direction, as I pointed out earlier. It can be from A to B or B to A. So, whenever a device is conducting, let us say it is in this position, that is A is connected to the top or a positive DC bus. So, this should be capable of conducting in both the directions. And if this is the connection, A is connected to the positive bus, then A is at the positive DC terminal and this is at the negative DC terminal, and you have a voltage of VDC crossing. So, between A and the bottom throw, there is a switch which is now blocking a voltage. This switch is in the off state, it is blocking a voltage. Voltage equal to what? Voltage equal to VDC. A similar observation can be made here. If you think that B is connected to the bottom throw, so this can be conducting and it should be capable of conducting in both the directions. So, the top throw is at a positive potential with respect to the pole and the voltage between the two is VDC. So, it again needs to be a switch which can block a potential of VDC, but with only one polarity. So, this is what we get here. This is the electronic realization. It can be conducting in either directions. The load current can be flowing in either direction. So, the transistor can conduct in one direction, the diode can conduct in this direction. Similarly, this transistor can conduct in this direction and the diode can conduct if it is in the opposite direction. If you look at the other state, then this transistor can conduct in one direction and this diode can conduct in the opposite direction. Again, this transistor conducts in this and this diode conducts in the opposite direction. So, this converter has an ability to apply a potential which is equal to that of this positive terminal or a potential equal to that of this negative terminal at A. It is capable of connecting this pole A to either the positive bus or the negative bus irrespective of the direction of current flow. The current flow could be from A to B or B to A. This is capable of connecting. That is the attribute of a voltage source inverter. It has an ability to apply a particular voltage out of a given set of voltages at a particular terminal irrespective of the direction of current. Now, here we have only two voltages available, which is namely this plus and minus. Later on when we go to a multi-level inverter, we will have more such terminals being available. So, this inverter has an ability to apply either this plus or minus, connect this pole A or the load terminal A to either this positive DC bus or the negative DC bus irrespective of the direction in which current flows. So, this is how you have a single phase voltage source inverter. You use bidirectional current carrying switches with unidirectional voltage blocking capability. So, if you have this kind of current conduction as I have indicated with this red ink here, what happens is B is now positive and with respect to here. So, the potential blocked here is going to be VDC. Similarly, this top switch is also off now, it is positive with respect to here now. You remember this is a single pole double throw switch. This is what the top and the bottom devices together are called one leg of the inverter. One leg of the inverter is a single pole double throw switch. We have realized a single pole double throw switch as two transistors which are switched in a complementary fashion. If the top switch is on, the bottom is off and vice versa, right. So, this is a single phase voltage source inverter now. So, let us look at a 3-phase voltage source inverter. What is a 3-phase voltage source inverter? Instead of 2 legs, it has 3 legs. Why? Now, you have a load which is a 3-phase load. The difference between the previous case and here is that was single phase, this is 3-phase. There we had a single phase load, here we are having a 3-phase load. A single phase load has 2 terminals, while a 3-phase load has 3 terminals. And the load is once again presumed to be inductive, and the inductive load has now 3 terminals. Therefore, the load terminals have all got to be connected to a pole each. One terminal of the load, let us call it R, is connected to one of the poles. Another terminal of the load, let us call it Y, is connected to another pole, and the third terminal of the load B is connected to yet another pole B. So, you have 3 poles and every pole has two throws corresponding to each of it. One throw is connected to the positive bus and the other throw is connected to the negative bus. So, one set of throws are connected together and connected to the positive bus, another set of throws are connected together and connected to the negative bus. So, this is what you have now. This is basically a 3-phase voltage source inverter represented in terms of generic switches. Now, we need to realize this electronically. It is similar to what we did before, because the current that you have at R, let us say, may be flowing in this direction or it could be flowing in the opposite direction. The same story about Y and B too. So, once again you need switches between the pole and the throws which are capable of conducting in either direction, and it all again needs unidirectional or unipolar voltage blocking capability. So, this is what you have now. Let us say R is conducting in this direction and let us say the top device is on. So, in that case you will find that this transistor is conducting and the bottom transistor will be blocking a potential equal to VDC. Let us slightly change the scenario and say that the current instead is flowing in this direction and the top device is on. In such a scenario, the top diode will conduct. Once again, the bottom transistor, this R is connected to the positive bus, the bottom transistor is going to be blocking a potential plus minus VDC like this. Let us consider yet another scenario. Let us say R is conducting in this direction and now the bottom transistor is on, the bottom switch is on and the top is off. If the bottom is on, you will have a conduction here and the diode is the one that will be conducting. In such a scenario, the top transistor is now in the off condition. So, the top transistor will be blocking a potential which is positive here and negative here, and the potential is equal to VDC. Similarly, let us say you take yet another scenario. Let us consider yet another scenario where the bottom is on, but the current flow is in the opposite direction. If the current flow is in the opposite direction, you will have current flowing through this transistor rather than through the diode, but the potential at R is equal to the potential of the negative terminal of DC bus. So, you will have the entire DC bus voltage appearing across the top transistor. So, the top transistor is still blocking a potential of plus minus VDC. So, whether the current is may be flowing in either direction. So, whichever is on, either the top or the bottom should be able to conduct in both the directions. So, you use a transistor with an anti-parallel diode. The transistor conducts in one of the direction, the anti-parallel diode conducts in the other direction. Of the two, let us say one of them is conducting, maybe the bottom, maybe the top transistor or the top diode. Let us say the top device is conducting. So, the bottom device is now in the off state and it has to block a potential. The bottom transistor simply blocks that potential. It's only unipolar. So, you have VDC coming across that, it blocks here. So, this is how you have all the 3 legs here, and so this is a 3-phase voltage source inverter and this is shown using IGBTs, right. Now, let us say this is a single phase current source inverter. You can see that structurally it is quite similar to a single phase voltage source inverter. What I mean, there is one with only one difference. In a single phase voltage source inverter, you had a load connected between these terminals A and B and you had a supply connected between these two terminals. Now, what we have done is the load which was inductive there has been replaced by a current source here, and the load is now capacitive and the capacitive load is connected across the throws. The current source, again the current flowing through the current source should always be provided with a path, it can never be opened, a current source can never be opened. So, the current pertaining it should always have a path to flow through. Therefore, the two terminals of the current source are connected to one pole each and there are corresponding throws and the load which is now capacitive is connected across the two throws. So, this is how what you have in a current source inverter now. So, you can see that this current is now it is only unidirectional current, it only flows in one direction now. So, if it is flowing in this direction, let us say this pole at A is connected to throw T1, then it has to conduct in this direction. It only has to conduct in this direction and not in the opposite direction. Similarly, you take this connection between B and T2 here, it has to conduct only in this direction. It never has to conduct in the opposite direction. Now, let us look at, let us just consider this scenario where the A is connected to the top throw and B is connected to the bottom throw and current is flowing like this. So, what happens to the switch that comes between A and T2? The switch is off. And what is the potential it sees? It sees the load voltage. The load voltage could either be positive or negative. So, what it sees is the load voltage, which is an alternating voltage. It could be of either polarity. Similarly, about the same thing about this switch also, which comes between B and T1. Here it is also in the off state, and what is the potential it sees? It again sees the load potential, because B is connected to T2, which is connected to the load. So, this is connected to the one end of the load, this is physically connected to the other end of the load. So, it may be like this, it is an alternating potential that it sees. T1 can be positive or B can be positive. So, it sees an alternating. So, now what you need is between A and T1 for example, or A and T2 for example, you need a switch which conducts in only one direction, in one particular direction, but you need a switch which can block voltages of either polarity. Hence, this is the realization. So, you can say if the current is flowing in this direction as it is, you will have, if these two devices are on, current flows in this direction, and this blocks a potential which can be of either polarity. A potential of this polarity is blocked by the diode, and a potential of opposite polarity could be blocked by the transistor, and therefore, you have a bidirectional voltage blocking capability here. Similarly, you can look at the other scenario where these two devices could be on. So, in that case current flows through this and here, and these two switches are now in the off state, which could be blocking a bidirectional voltage, which could be of either polarity. So, this is one electronic realization of a current source inverter. So, a single unidirectional current and bidirectional voltage blocking. As I mentioned earlier, thyristor is a natural option to do this, but we can also use a transistor in series with a diode, so called anti-series connection. Why anti-series? As I mentioned before, you may have something which can block in one potential and something another element which blocks in the opposite potential. So, let us say we take this transistor. This transistor is capable of blocking with this potential, whereas the diode is capable of blocking with an opposite polarity, while both of them conduct in the same direction. So, you call it an anti-series connection, and you go in for this and you get this done now, right. So, this is slightly redrawn. What you have here is, you see one transistor in one direction, another one. What we have done is, we have redrawn and the source is here and the load is there. We have brought the source to the left and load here. So, this is one leg of a current source inverter, very similar to one leg of a voltage source inverter. So, one leg of a voltage source inverter, if you remember it right, the fundamental difference is where the load was presumed to be inductive there. Here the load, a capacitance has been connected across the load. So, even if the load has some RL or whatever, if it is an RL load or whatever, it is overall it is capacitive in nature now, and you have a DC current source now. Apart from these differences, as far as the switches are concerned, earlier you had a switch which is capable of conducting in both the directions. Now, you have a switch which is capable of conducting in only one direction. Earlier you had in a voltage source inverter, you had a switch which can block or which needs to block a voltage of only a particular polarity. Here you have a transistor which can block with this polarity and a diode which can block with the opposite polarity, the two of them connected in series. You have a switch which has a bidirectional voltage blocking capability now. So, this is just the previous circuit has been redrawn. So, two things, this is only to see that you can add one more leg like this. If you want this is a single phase current source inverter. If you want a 3-phase current source inverter, all that you need to do is draw one more leg like this, and between those two legs also, let us call this R, Y and B. Between Y and B also you have capacitance, between R and B also you have capacitance, you have loads connected across them. There is a little more about single phase and 3-phase current source inverters. So, I have just drawn a single phase current source inverter using generic switch now. As I said, it is just that the same thing redrawn. So, this is a current source as 2 poles, as 2 terminals. So, these are connected to the 2 poles now, and the load, which is capacitive in nature, is connected across the throws, right. So, if you want to realize a single phase, or I mean from you want to realize a 3 phase current source inverter, the load is now 3 phase, it is a capacitive load. So, these are the load terminals, these are the 3 load terminals. So, the current source still has only 2 terminals. So, the current source is connected to, every terminal of the current source is connected to 1 pole each. So, the number of poles gets decided by the number of terminals of the current source, as I was mentioning in the previous lecture now. The number of terminals of the number of throws is equal to the number of load terminals, the load being capacitive now. So, you have 3 terminals of or 3 throws here. So, it is a single pole, double throw switch here, whereas it is single pole triple throw switch in the case of a current source inverter. So, we see such certain differences from the time when we are dealing with a DC to DC converter. In DC to DC converters, we only had single pole double throw switch, but now you are seeing a single pole triple throw switch in the case of a 3 phase inverter. And once again first in those cases the conduction was only in one direction, whereas in a voltage source inverter earlier we saw conduction in both the directions. We saw that the current carrying capability could be in either direction now. Again so that we are slightly expanding and going higher than this now. So, you had from a point where you used only a single pole double throw switch, which are all single quadrant switches. We again have single pole double throw switches in a voltage source inverter like here, but they have bidirectional current carrying capability. You have in a current source inverter, again you may have single pole double throw switch, unidirectional conduction, but bidirectional voltage blocking capability. And if you go to a 3 phase current source inverter, you will need 2 numbers of single pole triple throw switches. Now, all this is to recollect, and so that we have our ideas clearer before we launch onto whatever we need to see today now. So, that is about a multi-level inverter. A multi-level meaning, see, so far all that we have been seeing is we call that as a 2-level inverter. We have seen a voltage source inverter little earlier, we call that a 2-level voltage source inverter because let us say this potential R, take this pole R and look at the potential here, and this O, which is called the DC bus neutral or the DC bus midpoint, is a convenient point for us to express all the voltage, I mean as a reference to express all the voltages at various nodes now. This may not be physically available, but theoretically it is easy for us to mention now. So, the potential at R with respect to O can be plus VDC by 2 if R is connected to the positive throw. If R is connected to the bottom throw, it can be minus VDC by 2. So, the potential at R can take 2 values, either plus VDC by 2 or minus VDC by 2, and it can take only 2 values. Hence, we call this as a 2-level voltage source inverter. Alternatively, let us say if the same R, we have this R connected to a pole of a single pole triple throw switch rather than a single pole double throw switch, the same pole, but connected to 3 different throws. So, it is a single pole triple throw switch. Now, a single pole triple throw switch is available and you can connect it to any of these 3 throws now. In this case, what happens? The middle throw, it is connected to the midpoint here. Here, the midpoint is available for connection and a connection is made. In this case of a 2-level inverter, the midpoint is only kind of notional, it is only used for a theoretical purposes, it is not a physical point. You may not have that point available for you to make a connection, sometimes you may and sometimes you may not. But here you have this point is for electrical connection. So, you connect this to the midpoint of the 3rd throw or the middle throw, right. So, now what you have is a single pole triple throw switch, and VRO here can be, if the top is connected, it can be plus VDC by 2. If R is connected to the bottom throw, it can be minus VDC by 2 as before. If R is connected to the middle throw, it can simply be 0. So, VRO can take 3 values now, namely plus VDC by 2 or minus VDC by 2 as in previous inverter 2-level inverter, and also it is 0. So, it can take 3 different voltage levels, and therefore, we call this as a 3 level voltage source inverter. So, you have a set of 3 DC potentials available, which could be applied at this pole, namely plus VDC by 2 or 0 or minus VDC by 2. Again, this inverter, it is an inverter, it has a load, it is a voltage source inverter, and the load here is presumed to be inductive. And being an AC load, the current carrying, the conduction could be in either direction. It could be either flowing out of the pole or flowing into the pole. So, this switch or this converter should be capable of applying any of the 3 potentials, either plus VDC by 2, 0 or minus VDC by 2 at R, independent of the direction of current flow at R, because it is a voltage source converter. So, now what kind of switches do we need is the next question that we are going to look at for the next 15-20 minutes or so of this lecture now. Let us start this. Let us just look at every leg is now a single pole triple throw switch. The pole is connected to one of the throws, and between the pole and the other 2 throws the switches are open. Let us look at how to realize. Before we look at how do you go about realizing, let us try and understand why we need a 3 level inverter at all, because this is basic motivation, and also this is required for us to go about doing this realization partly. Now, one reason is it can give a better waveform quality, that is the potential at R, for example. If you want the potential at R, Y and B, let us say first say the potential between R and Y. This is one of 2 of those load terminals, and V R Y is basically a line to line voltage applied on the load. You want this voltage to be as sinusoidal as possible. You want it to be as sinusoidal as possible. So, you want the voltage to have as many levels as possible. In the case of a 2 level inverter, it can be either plus VDC or 0 or minus VDC. These are the only 3 voltage levels possible between VRY. If you take VRY, VRY can be either plus or minus VDC or 0 in the case of a 2 level inverter. In the case of a 3 level inverter, you have not only plus VDC 0, you can also have plus or minus 0.5 VDC. Let us say R is connected to the top throw and Y is connected to the middle throw. So, what you have between R and Y is plus 0.5 VDC. Not only that, let us say R is connected to the middle throw and Y is connected to the bottom throw, once again you can get plus 0.5 VDC. So, there are 2 different ways by which you can realize plus 0.5 VDC. Similarly, let us say you want to realize VRY equals minus 0.5 VDC, then what you can do is Y can be connected to the top throw and R can be connected to the middle throw. This will give you minus 0.5 VDC. Alternately, you can also connect Y to the middle throw and R to the bottom throw, once again it will give you minus 0.5 VDC. So, a 2 level voltage source inverter can give you only 3 different instantaneous values of line to line voltages, plus VDC, 0, minus VDC. Here you have 5 different values, plus VDC, plus 0.5 VDC, 0, minus 0.5 VDC and minus VDC. So, the sinusoidal voltage you want is at the desired voltage, and what we are going to apply is not going to be, it is not going to be the same as the desired voltage, but we can get closer to that because this plus 0.5 VDC and minus 0.5 VDC levels are available. Also, since there are 5 different voltage levels are available for this VRY, some authors tend to call this as a 5 level inverter. So, you need to be careful when someone tells you a 5 level or a 3 level, you need to understand what he is talking about. But in this course, we will always use this as a 3 level inverter. The number of levels we will define on the basis of the number of levels of the pole voltage rather than the number of levels of the line to line voltage. Here the pole voltage still has 3 levels only, and therefore, we call this now. So, the better quality waveform is because more number of levels are possible. So, you can follow a sine wave a little more closely than you could do with fewer levels. Let me put it even the other way. Let us say if VRY has to be sinusoidal, one way is VRO should be sinusoidal and VYO should also be sinusoidal. So, if VRO should be sinusoidal, once again you have a sinusoid here, you have a sinusoid here. Now, you have only potentials of plus VDC, minus VDC and 0. Now, you have 0 also for VRO. So, you have 3 different levels available. So, let us say at some instant this is your sign that you want, but what you apply is plus VDC. Let us say this plus VDC is here. and if you do not have plus VDC, the next level is minus VDC. You may be switching from here all the way down to minus VDC. We will do all this clearly in a later lecture. This will be minus VDC, and if I am applying minus VDC here, the error between what I desire, that is the sinusoidal waveform, and the error between what I actually apply, which is minus VDC, is very high. The error is VDC plus Vm, I mean where Vm, if I say, is the peak voltage of this sinusoid that I want now. Whereas, instead of applying 0, if I apply only like this, as shown by the red ink, if I apply only 0, the instantaneous error is now much lower. So, you can see that the instantaneous error between the ideal sinusoidal waveform and the actual applied waveform could be lower in the case of a 3 level inverter than in the case of a 2 level inverter. This is because more number of voltage levels are available. So, hence we say the output waveform could be closer to sinusoid, and therefore, we can say that it has a better waveform quality. The harmonic distortion could be lesser here. So, there is better waveform quality now. The another important reason why we use such a 3 level inverter is to be able to handle higher DC bus voltages. How do we do that? See, you have devices of various voltage ratings. There could be small MOSFETs which are rated for 60 volts or 100 volts or 120 volts. We have some IGBTs, and IGBTs could be rated for 600 volt and 1000 volt and 1200 volt and so on. You go on higher and higher, it is difficult to find devices of substantial voltage rating. So, we have something called as medium voltage drives. In motor drives, we have low voltage motors and we have medium voltage motors. These low voltage motors typically have voltage ratings of the order of hundreds of volt and just about 1 kilovolt or less than that. Medium voltage motors have voltage rating of the order of a few kilovolts, something like let us say about 2.2 kilovolt for example now. If you want to drive a 2.2 kilovolt motor using an inverter, you need switches of adequate voltage rating. Earlier we just saw in a 2 level inverter case that you need these switches which could block a potential of, if you take here this switch, if Y is connected to the bottom throw, then between the top throw and Y a potential of VDC appears. It has to block a potential equal to VDC. This VDC, if you want a 2.2 kilovolt motor, your VDC could be something close to 3 kilovolts. So, you may not get a switch which is capable of blocking 3 kilovolts. You will get I mean quite often you might be getting switches which can whose voltage ratings are substantially lower, or even if you have a switch which has a voltage rating higher than 3 kilovolts, it may be too expensive. Therefore, what you have is you have devices of given voltage rating. With this, you want to build an inverter whose DC bus voltage is significantly higher. So, you would normally go in for series connection of devices in such cases. Going in for a 3 level inverter is better than going in for a series connection, as I will point out now. A voltage level, I mean 3 level inverter can do equally well, and it is also better in some sense, as we will see a little later now. So, you can actually handle, you can build an inverter whose DC bus voltage is substantially higher than the device voltage ratings. That is one of the points that we are trying to make here now. Let us go further to see how we do what we do now. So, with regard to the electronic realization, what we need to realize is a single pole triple throw switch. So, we need to look at the individual pole to throw connections, pole to individual throws, connections between them, and before that let us look at the different states. So, this is what I call as state 1. It is a single pole triple throw switch. The pole can be connected to the 3 throws T1, T2 or 3. In this case, P is connected to T1. So, I am calling this as state 1. So, this is state 1. In this case, what happens? P and T2 are left open. Again, P and T3 are also left open. So, P and T2 is open, but it blocks some voltage. What is that voltage equal to? Voltage at P is equal to that of T, which is equal to 0.5 VDC, and the voltage at T2 is 0, and therefore, what you have is plus minus 0.5 VDC. The switches, I mean the switch or the set of switches that come between P and T2 are in the off condition, and they are blocking a potential. They are blocking a potential of this polarity as indicated, and they are blocking a potential of 0.5 VDC, right. Now, how about the switches between P and T3? Again they are off. they are blocking a potential. They are blocking a potential with P positive with respect to T3, and the potential difference is not 0.5 VDC, but it is entire VDC, because P is connected to 0.5 VDC and T3 is connected to minus 0.5 VDC. So, the potential difference is equal to VDC. This is state 1 of the single pole triple throw switch we are talking about. Now, let us look at state 2. This is state 2. Here, as you can see, P is connected to the throw T2. So, between P and T1 the devices are off. Similarly, between P and T3 the devices are off. So, between P and T1 the devices together are blocking a potential where T1 is positive with respect to P, because T1 is connected to plus 0.5 VDC, P is connected to T2 which is connected to 0, and the potential between these two is 0.5 VDC. Again, between P and T3 the switches are off, the devices are off. So, the potential is P is positive with respect to T3, and the potential difference between the two is once again 0.5 VDC. Once again you go to state 3, the pole is connected to the bottom throw T3, and between P and T1, T1 is positive, P is negative, and the potential difference is VDC. So, these switches are in the off condition and they are blocking a potential equal to VDC, and similarly the devices that come between P and T2 block a potential which is equal to 0.5 VDC here as indicated here. So, this is what you have now. So, let us go further and try to realize between P and T1. Let us try to see the kind of devices we need between P and T1. So, between P and T1 I have now given all the 3 states together. So, this is the on state, this is the on state as far as the switch concerned between P and T1 is concerned now. So, the current can be in either direction. So, this switch should be capable of conducting in both the direction. So, this is the requirement on the part of the switch or switches, the devices that come between P and T1. They should be capable of conducting in either direction. Now, let us say P is connected to T2. What should be done between P and T1? As I just mentioned before, P and T1 should be able to block a potential equal to 0.5 VDC with polarity as indicated here. T1 is positive with respect to P. Then, in the state 3, once again if you look at P and T1 it is off, and what is the potential? T1 is positive with respect to P, but the voltage now is VDC. In this second state the switch is blocking a voltage of voltage equal to 0.5 VDC. In the third state it is blocking a voltage equal to VDC, which is higher than the first one. So, what we need together is a switch which is capable of conducting in both the directions when it is in the off state, and which is capable of blocking a potential equal to VDC of this polarity that has been indicated here, T1 positive with respect to P. This is what we expect. This is the conduction, and these are the conduction and voltage blocking capabilities of the devices that come between pole P and throw T1. So, how do we realize this electronically? This is quite similar to what we saw in a voltage source inverter. So, the current could be flowing in either direction, and therefore, we have a switch which is capable of conducting in both the directions, which is a transistor with an anti-parallel diode. So, these two can conduct in both the directions. When this has to be off, let me indicate with a different color ink. When this switch is off, then T1 can be positive with respect to P, and the potential blocked needs to be VDC. So, these needs to be device you can have, if you have a transistor and a diode like this, and if the devices are rated for VDC, it should be possible for you to block this potential, right. Okay. So, the voltage rating of the device is VDC. You need bidirectional current, unipolar voltage, and the voltage rating of the device is VDC. So, let us move further. This is only one step towards the realization of a single pole triple throw switch. Now, let us look at the next one. Let us look at the conduction and voltage blocking capabilities between the pole P and throw T3. So, what we are looking as pole P and pole T3, this is now off state. Again pole P and throw T3, it is now in the off state, whereas this is the on state. In the on state, so there is always anyway current keeps flowing through the pole, and in the on state it flows through T3. Between P and T3 you need a bidirectional current carrying capability. So, once again you need a switch which is capable of conducting in both the directions. This is quite similar to what we had between pole P and throw T1. So, here if you say it is off, but if you look at the potential, the pole P is connected to throw T1 and therefore to plus 0.5 VDC, and so this is positive and throw T3 is negative. And what is the potential between the two? This is plus 0.5 VDC, this is minus 0.5 VDC, therefore, you have VDC is the potential coming across here. Once again you look at P and T3 in this state, pole P is positive with respect to throw T3. Now, P is connected to 0 and T3 is connected to minus 0.5 VDC, therefore, the potential here coming between the two is 0.5 VDC. So, the higher of these two if you consider, it is VDC. So, what you need is, you need a set of switches which are capable of conducting in both the directions here between P and T3, and again when they are in the off state, it should be capable of blocking a potential equal to VDC. So, this is what we might need, quite similar to what we got before. If it is conducting, these can conduct in these two directions. If it is blocking, it can block a potential like this. So, it is bidirectional current and unipolar voltage, and the voltage rating required is VDC. Right. Now, let us move on. We are still only inching our way towards the overall realization. Let us look at the conduction and voltage blocking capabilities between pole P and throw T2. Pole P is connected to throw T2 here. This is the on state, whereas it is open. P and T2 are open here also. So, these two are actually off states. In the on state, current can be flowing in either direction. So, between P and T2, current has to flow in either direction. So, once again what you need is, you need a bidirectional current carrying capability. You need bidirectional current carrying capability. Current needs to be bidirectional. How about the voltage now? Let us look at it a little carefully. It is off here, P is connected to T1. Therefore, P is positive and T2 is negative with respect to P. What is the potential that comes between the two? P is plus 0.5 VDC and T2 is 0. So, the potential difference is 0.5 VDC or VDC by 2. The potential difference is only VDC by 2 and not VDC, at P is positive with respect to T2. Let us look at this third connection. Here pole P is negative because it is connected to the bottom throw, which is connected to the negative bus, and T2 is positive. And what is the potential difference between the two? VDC by 2. So, now look at the difference. Now, look at the difference. Here the polarity is as indicated, and look at the polarity here. So, between P and T2, P and T1 was similar to what we had in a 2-level voltage source inverter. P and T3 was also similar to what we had in a voltage source inverter, but P and T2 is a little different. How? It requires a bidirectional or a bipolar voltage blocking capability. You need a bipolar voltage blocking capability. It is a bidirectional current. It is bidirectional current when it is on, and it is a bipolar voltage blocking when it is off. So, you need this P to T2 to be a 4-quadrant switch. Now, we discussed a 4-quadrant switch in our very first lecture. So, you need actually a 4-quadrant switch here to realize P and T2, whereas P and T1 and P and T3 are only bidirectional switches, 2-quadrant switches with bidirectional current conduction. So, now let us go about, we are still inching our way. Let us look at what could be a practical or feasible realization. It is a 4-quadrant switch. So, it can conduct in either direction. So, let us say it can be conducting either this way or this way. Let us first take that it is conducting in as indicated by red ink now. If it is conducting as indicated by red ink, then this is the direction of conduction. This is the direction of conduction. How about the voltage blocking? These two devices are in the off state. This is capable of blocking a voltage where the collector is positive with respect to the emitter. This diode is capable of blocking voltage where the cathode is positive with respect to the anode. So, together you can say that these two devices in series can block any bipolar voltage signal. This is what we need, the 4-quadrant switch, we need this bidirectional. So, let us say if the current direction is the other way, let us say the current direction is the other way, then what happens is these two conduct, this bottom transistor and the diode conduct, and now the top collector is capable of blocking a potential as indicated here, and the diode is capable of blocking a potential like this. The two in series together can block a potential either way. Now, the voltage rating required is only 0.5 VDC. You need to block a potential of only 0.5 VDC. So, you do not need a switch which is capable of blocking VDC or whose voltage rating is equal to VDC. Please remember, the voltage rating of the switch has always got to be substantially higher than VDC or 0.5 VDC, because there are going to be over voltage spikes and several things, but still this is an important factor. So, this is one of the reasons why you choose now. For example, if you need about, let us say, 700 volt DC bus, which is very common in India, we use 400 or 415 volt kind of motors. We want to drive these motors, we will commonly use a DC bus voltage is equal to about 700 volts now. For 700 volts voltage rating or voltage bus, it is very common to use devices that are rated 1000 volts or 1200 volts. 1200 volts is even more common. I think that is probably because of the availability of devices now. So, if you use 1200 volts for 700 volt rating, here if you say your DC bus voltage is only 350 volt for example, you will still require something like 600 volts. So, for a 700 volt DC bus rating, you will still use 1200 volts because of practical considerations. Right now, we are ignoring all those practical considerations and we are just looking at the device voltage rating as it should be in an ideal scenario. So, here what we see is these devices need not be rated for the entire DC bus voltage, it is enough if they are rated for half the DC bus voltage now. Thus, we have some idea now between how the switch should look like between P and T1, P and T2 and P and T3. Let us put them together now. So, all these switches are capable of bidirectional current conduction, because through pole P the current conduction can be in both the direction. You can see that all these switches can conduct in both the directions. This can conduct this way, this can conduct this way, this transistor like this diode like this. This can conduct in this direction, this can conduct in the opposite direction. All these three switches are capable of conducting in both the directions now. About voltage blocking, well, this can block only with this polarity. This also can block only with this polarity, whereas these switches can block with both the polarities. So, these are two quadrant switches, the top and the bottom. The top to middle is a 4 quadrant switch as I mentioned earlier now. And the voltage rating of P to T1 has to be VDC. Here again it has to be VDC, whereas here it is only 0.5 VDC. It has to block only 0.5 VDC. So, we want to realize a single pole triple throw switch not with devices of voltage rating VDC and some devices with VDC by 2. We want to realize this with all devices whose ratings are only equal to VDC, whose ratings correspond to VDC by 2. So, what we do is like this, go in for a series connection just to start with, so that one of them is capable of blocking a potential VDC by 2 and the other one is also capable of blocking a potential equal to VDC by 2. So, the two together in series can block a potential equal to VDC. This is just an idea, we are still moving towards what is going to be our final circuit now. Again the bottom devices also you have two of them in series now. So, now what you have realized a single pole triple throw switch starting from fundamentals as we have been doing for DC-DC converter and then for the 2 level voltage source inverter and current source inverter, we have been doing this. So, now we have come to some kind of a realization now. So, we are able to realize this using transistors and diodes that are rated for only VDC by 2 and nothing higher than that, not equal to VDC. So, you use devices of lower ratings to handle a DC bus voltage which is substantially higher, right. Now, what do we do? Do we need all this? How is it going to be operated? If pole P is to be connected to throw T1, let me just give some names for this. Let me call the switch as S1, call this as S2, this as S3, this is S4. Let me call this switch as S2A and S3A. I have there some meaning behind this. I am not calling it as something different, but I am saying it is something because it is something related to S2. Let us get there in a short while from now. If you want pole P to be connected to throw T1 with such a realization, with such kind of switches, what do you have to do? Both S1 and S2 have to be on and both S3 and S4 have to be off. And similarly, S2A and S3A also needs to be off now. So, again if you have to connect to the bottom throw T3, S3 and S4 should be on and all the other switches should be off. if you have to connect pole P to throw T2, only these two switches S2A and S3A should be on, all the other 4 should be off, right. So, this is how you realize, but the question now is, do you really need this kind of a realization? Can it not be a little simpler? How can it be a little simpler? Let us look at an individual switch now. Why do we need a switch? We need a switch, number 1, to make a contact, number 2, to break a contact, or to open. So, either it provides the connection between two of its terminals or it opens out. So, let us say you take the switch S1 and S2. Now, S1 has a role, one is to connect the throw T1 to this terminal here. The other function it has is to open, to serve as an open circuit between, open connection between these two terminals now. Now, let us say if you want to connect pole P to throw T1, you have to, both of them have to be on. If you want to disconnect pole P and throw T1, it is not necessary that both of them needs to be on. It is enough if S1 alone is off and S2 could still be on, right. Only if both the switches are on, it could be conducting now. So, there is some redundancy here. Now, similarly, let us say if S2A is, these two are conducting, these two S1 and S2 are conducting now. If S1 and S2 are conducting, what is the potential here at the midpoint? Plus. What is the potential here? This is 0. So, who is blocking the voltage between these two? Is it the transistor or is it the diode? It is actually the diode that is blocking this potential. So, this transistor does not have a significant role in blocking the voltage, blocking is actually done by diode. So, we go to the question whether we can have any reduction in the number of transistors, whether we can have any reduction in the number of transistors now. So, there seems to be some kind of redundancy, because if P and T1 needs to be opened out, it is enough just to have S1 opened, need not have to open both S1 and S2. Similarly, if P and T2 are opened, if P is connected to positive through T1, then this is what serves as the open circuit, the diode is what is providing the voltage blocking capability required, not the other way. So, the question is, what happens if we connect these two? What happens if we connect these two? It can still work. Pole P to throw T1, if you have to do, what you do is, and S1 and S2 are on, you have S1 and S2 are on, pole P and throw T2 will be connected now. For P to T1 to be connected, what you do is S1, S2 on. For pole P and throw T2 to be connected, what you do is you have S2 on, and let us call this as S3 and S4. We can also have a similar connection coming between here now. So, if you have this S2 and S3 are on, it can provide a connection with S1 being off. And pole P to T3, you can say S3 and S4 are on, the other switches are off. So, you can actually connect these two, or you can replace these two switches, these two transistors, what I had called as S2A and S2 by a single one, and S3A and S3 by a single transistor as shown here. And now, this is what I would call as the final realization of a single pole triple throw switch now. This is the pole P, this is the throw T1, this is throw T2, this is throw T3. This is connected to the positive terminal, this is connected to 0, this is connected to minus. So, you have S1 and S2 on for connecting the pole to the top throw, S3 and S4 on for connecting the pole to the bottom throw, the other switches are off. If you have to connect the pole to the middle throw, then you keep S2 and S3 on. So, the current flow, if at pole is like this, if you are connected to T2, then the current will choose to flow like this. If your current is in the opposite direction, if it is in the opposite direction, then it could flow like this. So, this provides a bidirectional current path. So, you are able to connect this DC bus neutral to the pole P, and therefore, one of the names that is given to this circuit is a neutral point clamped inverter, as we will just see a little later. And you use a diode to make this connection, and therefore, it is called a diode clamp inverter now. So, what you find here is S1 and S3 are actually complementary. If S1 is on, S3 will always be off and vice versa. If S1 is on, S4 will always be off and vice versa. So, this is a neutral point clamped or diode clamped inverter, because as I just mentioned, the DC bus neutral can get connected to this pole through these two by keeping S2 and S3 on, and or it is called diode clamped inverter because diodes are used to clamp that off. We just look at our last slide. So, this is I have just indicated for single phase loads here. So, it is just a connection for meant for a single phase load. You have two different legs here. You could also have three different legs potentially for a 3 level diode clamped inverter. We will discuss more on multi-level inverter. There are several other configurations are also that are available now. This is one of the most commonly used combination, that is a neutral point clamped or a diode clamped inverter. We will be discussing this further and other configurations of multi-level inverters in the next lecture. So, thank you very much for your patience and your interest, and I look forward to further lectures, and I hope you found this interesting and useful. Thank you very much.